Okay. All right. So what I'm using here today for the review is just the practice final exam, which is on the Blackboard page under the sample test, right? So so that's what I'm looking at, and I'm not going to do all the problems, but remember we're going to do quite a few of them, time permitting. But but remember the answers are at the end. Well, I'm not going to scroll all the way to the end, but if you go to the end of this document, there's the answers, but it's just short answers. It's just the final answer. So there's no solutions, right? So so watch carefully and ask questions. So you can hear me talk about the solutions. If we have time, I'll also look at problems from those last two homework assignments. The ones on rational functions and polar coordinates, which are due on Wednesday. But there are some problems on the review about polar coordinates and rational functions also, plus the test 3 review. Don't forget the review for test number 3 had problems about also about rational functions and polar coordinates. So you can go back and look at that as well to help you prepare for those questions that are on the final exam. Hello, Muhammad. Okay, so I'm going to start here, and we're going to start right at the beginning at number 1. Just to remind you of something that we did way back at the beginning of the class, but it's important so so that you will not mess up this easy questions on the final. If you're going to miss some questions, make sure you miss the hard ones, right? Not the easy ones. Okay, so most people do this pretty easily, though. If there's a question like this on the final. So, but now don't think that every question I'm going to go over is necessarily going to be on the final, or vice versa, right? There still may be some things on the final that we've talked about in class that I don't get to today, right? Or are not explicitly covered on the practice exam. So you also need to look at your previous tests and your previous practice tests and your homework, right, in studying for that final on Wednesday. And don't forget to come at 9:45, right? 9:45. Try to make it by 9:45 because that's when we officially have to start. That's when the final exam period starts. It's slightly off time this time. Okay, so in this problem, it says the birth weight of a child is often used to predict the overall health of the child during infancy. So usually doctors want the birth weights to be higher, not lower. And it says the typical birth weight of a baby is influenced by the number of visits to the doctor that prenatal visits that the mother can make to the doctor. So mothers who visit the doctor twice during pregnancy can expect to have babies weighing 5.8 pounds, but mothers who visit the doctor 4 times can expect babies to weighing 6.2 pounds, right? And so after all that long setup, it says, assume that the typical birth weight of the baby, which we're going to call Y, we're going to call that value Y, that steadily increases as the number of doctor visits increases. And we're going to call that number of doctor visits X, all right, just to give that quantity a variable name. And so there's your quantity Y and there's your quantity X. And it says, first question, this is just a thought question, right? Why are we justified in assuming that the relationship between Y and X is linear? What is it in that setup that lets you know that that quantity Y and that quantity X are related by a linear relationship? The steady increase, right? Yeah. So you know the fact that Y is increasing steadily as X increases, right? The birth weight is increasing steadily as the number of visits increases. So that's all you need to say here. So if you look at the answer key is going to say something like what Hannah just said, right? We know that the birth weight is increasing steadily as the number of doctor visits increases, right? And now next is a little bit more mathematical. Find the slope, right? And then find the slope, and then let's interpret that in what the meaning of that slope is in a practical context. So this is just using the slope formula, right? So to find the slope, you want to use the slope formula, right? So you guys all know the slope formula very well, right? From our lots of experience in calculating slopes, right? So there's the slope formula. But we just have to know what x1, y1, and x2, y2 are, right? And those are coordinates for points on the line. But we know coordinates for points on this line, right, Muhammad? We know 2 points on this line. So, and that because that's from the information that we're given, right? So, Muhammad, what would a couple of points be on that line? Say that again for me now. Okay, well, 5. Okay, those are birth weights, right? But in your coordinates for points, right, you need both an x coordinate and a y coordinate. So you're telling me the y values, which are birth weights, but I need x values that go with those, right? So think again there, right? Hi, Iris, and I think Giselle also is here online. Yeah, go ahead, Mohammed. So for instance, when the y, for instance, when the y value is 5.8, right? Right, when the birth weight is 5.8, what's the x value that went with that? 2, yeah, right. It's 2, yeah, right. Okay, and then for the birth weight of 6.2, the x value is 4, right? Okay, 2 doctor visits typically, leads to a birth weight of 5.8. 4 doctor visits typically leads to a birth weight of 6.2, right? And so those are the values you can use in your in calculating your slope, right? So you have 6.2 minus 5.8 over 4 minus 2. So you just get a really easy calculation here, right? It's 0.4 over 2, which is 0.2, right? Okay. Now, what's our interpretation of that, however? So what's that 0.2 telling us, right? So it's telling us something about the increase in the birth rate, right? Okay. So Hannah, can you say that? Right? When which is the number of doctor visits. So when the number of doctor visits increases by what? 1. Exactly right. Remember, slope is always x increasing by 1. So the birth weight goes up by typically, right? These things are all just averages, but the birth weight goes up by 0.2 when the number of doctor visits goes up by 1, right? So presumably that's because the mother is monitoring the health of her child more, right, and taking whatever steps are necessary, right, to make sure she has a safe birth, right? And now write the equation for the line. So we just have to remember our different forms for the equation for the line, right? One of them is our favorite. That's the slope intercept form, right? Where you know the slope and you know the y-intercept, but here we don't really know the y-intercept, right? So, but we can use the other form, right? Which was what? Y is equal to m times x minus x1 plus y1, right? And here x1, y1 are any point on the line, but we have 2 points on the line, right? So we got plenty of options, and we know what the slope is, right? That's 0.2. So we have y is equal to 0.2 times x minus, let's use the first point, 2 plus 5.8. Whoops. Why did that do that? Is that still showing up there? Okay, I don't know what I did. Plus the 5.8. I thought my power was going to go out again, but do I have this plugged in? Yes. Okay, well, worry about that when it happens. All right, so so there's the first problem. So to make a long story short here, make sure you know how to write down equations for lines, right? Okay, so make sure you know how to calculate slopes, right? And then once you have the slope, right, make sure you know how to use the slope, right, and then a point on the line, right, to write down the actual formula for the line. Okay, that's just a very basic skill, and certainly going to need it in calculus for sure, because you have to write down equations for lines all the time in calculus, and the instructor is just going to assume that you can do that really fast. All right, so let's look at point number 2, because this is the same sort of problem. It's just in a slightly different context. So find the equation for the line that is perpendicular to the given line. So here we have a formula for a line, right? And we want to find the equation for the line that's perpendicular to this line, but contains the point 2, 2, right? So when we're thinking about this problem, right, what we're thinking about is, I need the equation for this line, and that means I need to know a point on the line, but I've got a point, right? But I need to also know the slope of the line. But you're going to get the slope of the line from the fact that the line that you're looking for is perpendicular to this given line, right? Okay, see, that's the secret. And we know there's a relationship between the slopes of perpendicular lines, right? So let's find first the slope of this line, the line that we're given. That's easy to do, because if you just add 2x to both sides, you get y equals 2x plus 4, and that's in slope-intercept form. And when it's in slope-intercept form, then you can just read off the slope of the line. So, so the slope of this line is 2, but that's not going to be the slope of the line that we're interested in, right? Okay, because the line that we're interested in, is perpendicular to this line. So, so the slope of that line is going to be what? What's the relationship between the slopes of perpendicular lines? For parallel lines, they're the same, so that's easy relationship. But what is it for perpendicular lines? So here's one thing to either force yourself to memorize or write on your survival card, right? For perpendicular lines, they're negative reciprocals. Negative reciprocals. So if this line has slope positive 2, this line is going to have slope the reciprocal of 2, which is 1/2, and then you have to change the sign, so it would be -1. And then you're done, right? Because now you can write down the equation for the line using the same idea that we did in the first problem, right? You have the slope times x minus x coordinate of a point, and then plus the y coordinate of that same point. So there's the slope of the line, and you can just leave it like that. Unless it says simplify it for some reason, you're done, because that is the equation for a line. Okay. So remember about equations for lines, and then remember about graphing lines. So I'm not going to graph this one for you right now, because this is a very basic sort of problem. But you think about this one when you're preparing for a test. Make sure you know how to graph lines. Okay, so it wanted you to graph both of these lines on the same set of axes, right? What are the two lines? This line and then this line that we just discovered, right? So just build a table of XY values for those two lines, right? Okay, how do you build a table of XY values? Well, just, pick an X value and find the matching Y value. For this line, just, if X is 0, Y is going to be 4. If X is 2, Y is going to be 8, right? So it's easy to find points on this line, easy to find points on this line, same idea, just plug in an X value, find a matching Y value, plot those points, and then connect them with a straight line. So if you look at the answer key, you'll see the graphs of those two lines. Remember, they were supposed to be perpendicular. So when you make the graph, if you don't come out with perpendicular lines, that means they meet at an 90-degree angle, right? If you don't come out with perpendicular lines, then you go back and look again. Okay, so I'm not going to do 3 and 4, these simple problems where it just says, convert angles between radians and degrees. You know how to do that, or calculate, sines and cosines of, various angles. look carefully though, because here it's asking you for inverse sine or inverse cosine, right? Okay, so pay attention to those. But here's one that I know that everyone can do, and I'm pretty sure this is on the final because this is such a basic trig problem. So here's one that everyone should get. So in this picture, let's see, it says at a distance of 20 yards from the base of a tree, the angle of elevation to the top of the tree is 40 degrees. So you see this picture, right? Okay. And we want to know what the height of the tree is. So if you're wondering about how to measure the height of a tree, if you don't want to climb up the tree, you can do it with trigonometry, right? Okay. But you have to be able to do a little bit of surveying, all right? Because you've got to also have to be able to find this angle of elevation from the ground to the top of the tree at some distance away from the tree. So here the distance is 20 yards, right? Okay. And so, you know, assuming the tree is growing up pretty straight, right? We have a right triangle in this picture, correct? With one of the acute angles that's embedded in the right triangle. So we want to use some trigonometry with this particular angle, correct, to find the height of this tree. Let's call that height h. And so from this picture, what trigonometric ratio can we write down here? What with respect to that angle 40 degrees, what values do you know here? Well, not cosine, right, Robbie? Because to write down the cosine is adjacent over what? Yeah, over hypotenuse, but we don't know the hypotenuse, right? Well, I guess we could label it, okay? But that's not really what we're looking for, right? Okay, we're looking for the height. So Irish, yeah, you're right. It's tangent, correct? Because tangent is the most direct way of getting to the h, because tangent is opposite over adjacent, right? So so we know that the tangent of 40 degrees is h opposite over 20. And now just solve that equation for h, right? Which is trivial. You just multiply both sides by 20. So you have 20 times the tangent of 40 degrees. And now you just use your calculator to estimate the tangent of 40 degrees, right? And multiply it by 20. So you can look on the answer key and see what that result turns out to be. So I think now this is similar, except here instead of so number 7, here instead of looking for the length of one of the sides of this right triangle, right? Now we're actually looking for the angle that's embedded in the right triangle. But we still use, you know, just trigonometry, correct, to find this. And Iris, I think in this picture, we're kind of in the same situation, aren't we? Because with respect to theta, what do we know? The opposite and the adjacent, correct? Right? So so we can immediately write down that the tangent of theta is 15 over 10, which is, I guess if you want to reduce that, it's 1.5, or you can also write it as 3/2. Now, so this leaves us with an equation to solve, right? Because we have to solve for theta, since that's what we're asked for in the problem. So that means we have to get the theta out of the tangent. How do we do that? Inverse, right? So you just apply the inverse tangent, right? So you have inverse tangent of theta is equal to the inverse tangent of 3/2. And of course, here the tangents now will undo each other. They'll cancel. So you'll get theta. And now you're left with your trusty calculator, right? This is not going to be a special angle. I don't know of a special angle whose tangent is 3/2. So I'm going to have to use the calculator to compute the inverse tangent of 3/2. Inverse tangent of 3/2. What would that be? So 56.31. Okay, so in degrees, 56.31. Okay, Of course, on the final, right, like on the previous test, if you're given instructions about degrees versus radians, make sure you follow those instructions. Here, I don't think you're given any instructions. So if you want to write that down in degrees, that's fine. Okay, but you could also write it down in radians. Well, then this problem 8b is going to be very similar, right? Because here we're solving an equation that involves sine, and when we're solving for x, right? But we have sine of x in the equation. So that means at some point we're going to have to use inverse sine, right? To get the x out of the sine. But we have to do a little bit of work first, right? To do that. So let's see, we have 3 sine of x minus 1 squared is equal to 0. The first thing that's bothering me here is the square. So I would like to get rid of that square. Now, you can get rid of the square by multiplying out this the parentheses on the left-hand side. In other words, you can expand this product on the left-hand side, but that's not what you want to do, okay? Because you're going to make your life miserable. Okay. When you have a quantity squared equals 0, right? Then that quantity, see, that's what we had here, right? We have this quantity squared is equal to 0. Then that quantity's got to be what? What's the only number squared that gives you 0? 0, right? Yeah. Okay. Only 0 squared is 0. So see, you can immediately deduce that 3 sine of x minus 1 is equal to 0. So you don't really have to expand this product at all. Okay, you can easily dispatch the square here just by noticing. Oh yeah, if 3 sine of x minus 1 squared is equal to 0, then 3 sine of x minus 1 has to be 0. Another way of thinking of that is you can think of taking the square root of both sides. So you can think of taking the square root of both sides. But when you do that, make sure, so if you take the square root of both sides, make sure that you remember that numbers have 2 square roots. One of them is positive and one of them is negative. However, in this case, the square root of 0 is just what? No, the square root of 0 is 0. And plus or minus 0 is still 0. So the plus or minus is not meaningful in this example. So to make I took a long time to explain what you probably already realized, right? That just 3 sine of x minus 1 is equal to 0. You know that. So the square is kind of, not meaningful in this problem. Now we continue here, right? So we have 3 sine of x is equal to 1. I'm going to bring the 1 to the right hand side and divide by 3. So now I have sine of x is equal to 1/3. And now finally I'm in a position to apply the inverse sine. So I have sine inverse of sine of x is equal to sine inverse of 1/3. And so we have x is equal to sine inverse of 1/3. That gives us one solution to this equation. But there are actually infinitely many solutions to this equation because sine is periodic, right? When you graph the sine curve, it's periodic, right? It keeps repeating the same values over and over again. So this equation has lots of solutions. But fortunately, you were told you just need one. Okay, so one solution is fine here, and so there it is. You can use your calculator to get the inverse sine of 1/3. What does your calculator say? Sine of 1/3 is approximately in radians. Point what? 3.34. Okay. So that's it. So we don't have to find the remaining solutions here. One way, of course, to get more solutions is just to add on multiples of 2 pi, right? But then remember you can look for more solutions as well to that equation. Now here is a tough one. All right, so this one is fun, but it's not really bad. You just have to look at it in the right way, and does take some steps, but you can do it. Okay. so we've got two lines here that are drawn, and they're apparently not perpendicular to one another, right? They do not, that doesn't look like they meet at a 90-degree angle. So we actually want to find what is the angle between those two lines, okay? It doesn't look like they're perpendicular. What is the angle where these two lines meet, okay? So we're trying to figure out what is that value for theta. And we only know how to find values for theta, I think, if they're in triangles, correct? So we need to put a triangle in here. So somehow we need to superimpose some triangle in this picture. Lots of ways of drawing a triangle in the picture, right? But y'all have any suggestions for how we could put a triangle in here? I'm thinking just use the x-axis right there. So I'm going to draw a line on top of the x-axis right there. And now I'm looking at this triangle. See that little wedge triangle right there? Okay. So this is shaded in there a little bit. So I'm looking at this triangle because that does have theta as one of the angles in that triangle, correct? But that's not a right triangle, but it is a triangle, right? So and it does contain that angle theta that we're looking for. And we know something else about this. We know something else about this triangle, but not much else, right? But we know something else. We know the length of this side, don't we? Yeah, the length of that side is 2. That's easy to see. That's 2. Now, to find theta, I want to use the law of cosines, okay? So that's the instruction in the problem. And since this is not a right triangle, that's really our only hope, because that's all we've learned about it, of course, right? Is in addition to right triangles, for triangles that aren't right triangles, all we know really is the law of cosine. So I really have to have the law of cosines here. So so let's label the sides here. And let's also label this angle theta. So this angle theta, I'm going to call that, for this triangle, I'm also going to call that angle A. All right. And so we label the side opposite angle A. What do we label that side? We label that little a, right? In the law of cosines, we label that little a. So we know something about little a. It is 2, right? Now, the other two sides we usually label B and C. Doesn't really matter which one we call B and which one we call C. So I'm going to call the one up here B, and I'm going to call the one down below, right? A little bit below that. Let's call that C. So according to the law of cosines, I would know that little a squared is equal to little b squared plus little c squared plus, no, not plus, right? Minus 2bc times the cosine of what? A, right? But a here is theta. So I can write theta there instead of capital A. And now I'm sort of in good shape, right? Because I've got now this equation that involves theta. And so maybe I can solve that equation for theta. But to solve this equation for theta, I've got to know what the A, B, and C are. But I know the A, right? The A is 2. So I'm making some progress. I just don't quite know the B and the C. So how can I figure out the B and how can I figure out the C? So the distance formula, yeah, we can use the distance formula here, right? Okay, so let's use the distance formula to find the length of B and the distance formula to find the length of C. All right, so let's think about the distance formula for the length of B. So the length of B would be what? Well, B connects these 2 points, right? These 2 points. So we're just trying to find the distance between those 2 points, correct? And we know, according to the distance formula, that's going to be the square root of, so what do you do in the distance formula? You take, don't you take the difference in the x coordinates, right? And you square that plus the difference in the y coordinates, correct? And you square that. Well, I got to think about what these x coordinates are, right? So what was this point? Do I have room to even write that in there? I'm running out of room here in this picture, but what is that point? Was it -4? Yeah, and 0, right? So -4 and 0. What was this point up here? 0 and what? 4. Yeah, 0 on the x-axis and 4 on the y-axis. Oh, so that should be pretty easy. So what is that? -4 minus 0, right? Difference in the x coordinates. -4 minus 0, square that, plus the difference in the y coordinates, right? So that is what? 0 minus 4. And square that. So I get b is equal to the square root of, and now I have what? -4 squared, that's 16. This is -4 squared again, 16. So it looks like b is the square root of 32. Square root of 32. You can simplify that if you want to, by the way. Square root of 32 is 32 is 16 times 2, right? And the reason I would write 32 is 16 times 2 is 16 is a perfect square. So you would end up with 4 times the square root of 2. All right, now let's do it now let's find C. What's this point? This is -2 and 0, right? And same point on top. So we know, if I can squeeze that, let me put it down here. So we know that C is going to be the square root of, see, what is that? -2 minus 0 squared, right? Plus again, 0 minus 4 squared. So we get the square root of -2 squared is 4, -4 squared is 16 again. So you get the square root of 20. And square root of 20, if you simplify that, you end up with 2 times the square root of 5. If you want to, but you could leave it as square root of 20. That would be fine. And there it is. So there they are, right? There are the numbers you're going to plug into your, there are the numbers that you're going to plug into your law of cosines. Ooh, that's going to give you some arithmetic. So you have 4 square root of 2 squared plus 2 square root of 5 squared minus 2 times this times this. And then don't forget that's multiplied times the cosine of theta. So it looks like I get 4 is equal to, well, when you square 4 times the square root of 2, you get 32. Because remember, this was the square root of 32. So when you square that, you get 32. Plus, when you square this, you're going to get 20. Because 2 times the square root of 5 was the same as the square root of 20. Square root of 20 squared is 20. And then minus, and now you're going to need your calculator to help you this part, though. Somebody want to help me with that? That's 2 times the square root of 32 times the square root of 20. It's also, by the way, 16 times the square root of 10. I'm going to shift things around a little bit. This is what I got. just doing this by hand without the calculator, I got 3 over the square root of 10. 3 over the square root of 10. 3 divided by the square root of 10. Be close to 1, but not quite. 0.948. So I get that cosine of theta is 0.948. Did anyone else get 0.948? You don't have to do it the way I did it. Okay. I mean, you can start making your, you can make your decimal estimates different. Okay. But I got that cosine is 0.948. I wonder if I did that right. I did kind of quick there. So not sure if that's correct. So, but you don't have to do it like I did it. Just once you've got these values filled in, you can start using your calculator to help you with your decimal approximations, right? And hopefully you will eventually come up with cosine of theta is approximately 0.948. And then what you do, of course, here, just apply what? Yeah, you just apply inverse cosine, right? Okay, so just take the inverse cosine of 0.948, right, to get theta. So what does that end up to be approximately? Very small angle. What is that in degrees? What now? 18.4? Is that what the answer says? Yeah. Okay, so, oh, all right. So, but you got slightly different there, Iris, but probably that was just because of rounding at some point. All right, so I see, right, around 18.5, 18.4, something like that is what you're going to come up with, depending on how you rounded these numbers. All right, but does that make sense now? Once you filled in the values, can you do the arithmetic from that point? Okay. I mean, I did it sort of as much by hand as possible, but you don't have to do it as much by hand as you can. You can start making decimal approximations sooner, right, than what I did. That's probably the lengthiest problem on the review, okay? But it's just a law of cosines problem. All right, let's try 10b. Here we're just solving a logarithmic, equation. So let's see if we can do this one. So guys, what are we going to do first in solving that? What are we going to do first in solving that logarithmic equation? What's going to be our first step? Combine. Yeah, you want to combine the logs, right? Now, I threw a little bit of a curveball at you here in this problem, because this is natural log of 3 minus x minus the natural log of x. Most examples we've seen natural log of quantity plus natural log of another quantity, okay? And when you have the sum of two natural logs, remember that's the natural log of the product. But here we have the difference of two natural logs. So how do you combine those? How is that different? This would be the natural log of what? Instead of multiplying these two quantities together, what do you do? What? What'd you say, Alexander? No. If you have the sum of logs, then you multiply. You divide, right? But with difference of logs, you divide. So this would be the natural log of 3 minus x over x, instead of 3 minus x times x is equal to 0. So Iris, you're right. First you have to combine them, okay? And then, now how do we get rid of the natural log? See, that's the real key step here, is getting rid of the natural log. So how do we get rid of that? Yeah, you apply the inverse. What's the inverse, Hannah, of natural log? E, right? So it's exponential, natural exponential function. So you raise both sides to, or raise e to both sides, okay? So on the left-hand side, that's easy. You just end up with 3 minus x over x. and it's on and then you have to just compute e to the 0, but that's also easy on the right hand side because any number other than 0 to the 0th power has got to be what? 1. So you end up with this very easy equation: 3 minus x over x is equal to 1. Just multiply both sides by x then to get rid of the fraction. And so you get 3 minus x is equal to x. And now add, take this x to the right-hand side. So you get 3 is equal to 2x, or it looks like x is 3 halves. So you just get one solution there, x equals halves. Now, in 11, we're going to solve not a logarithmic equation, but an exponential equation. But it's in a word problem. So let's read the word problem here. It says the first known radioactive element, radium, was isolated by Marie Curie in 1898, and she was the person who coined the term radioactive. Because it came from this, because she isolated this element, radium. This was a major event in science, and it took Marie Curie a long time. Her and her husband, they worked for many years to isolate this very small sample of radium, 1 gram, only 1 gram. It took them several years to do that. So what this formula tells you, though, is the amount remaining of 1 gram of radium after a given number of years. So the amount is in grams, and the elapsed time here is years, okay? And radium is radioactive, so the amount dissipates, okay, over time, all right? It doesn't evaporate, kind of like evaporating though, but the atoms, the radium atoms are actually breaking down, right? Okay, so the subatomic particles are dissipating in the atoms of radium, and that's why radium is dangerous to you, because those subatomic particles next to that radium for a length of time, the subatomic particles will interact with genes, and they will make you sick, cause you to develop cancer, which is exactly what happened to Marie Curie, right? But what we want to know is how much remains after 750 years. Okay, so radium dissipates slowly. Okay, it doesn't dissipate quickly. So how much is left after 750 years? That's easy, right? Because here you know the value for t, right? You're given the value for t, so you're just doing a straightforward calculation here, right? A little bit complicated because this exponent in this exponential function is so small, but other than that, it's just a matter of using your calculator. So just substitute the 750, right? Multiply it by that small coefficient there, and see what you get. That coefficient is called the decay rate, by the way, of the radium. So you can see the answers there on the answer key. We don't need to go through that calculation. What does the answer sheet say? Does anyone have the answer sheet to look at?
All the way at the bottom.
Yeah, all the way at the bottom. This is 11A. 0.72 grams. Yeah, so see, we only started with 1 gram, and after 750 years, we still have 0.72 grams there in that sample. So see, it decays slowly, right? Now, however, the next question is more interesting. It says, how long does it take for the sample to dissipate by 1/2? So how long would it take for that 1 gram of radium to reduce to 1/2 of a gram? That's called the half-life of the substance. So radioactive substances have half-lives, and that's what we're computing here, how long it takes for an amount to dissipate by 1/2. So in part B, right, what we're given is not the time, right? We know the amount that we want, right? We want the radium to dissipate to 1/2 of a gram. So we would fill in 0.5 for the amount, and then we would have this equation to solve, right? To find the t value, the amount of time, right, that is required to get us down to 1/2 of the gram. So you just fill in 1/2 for the y, and then you're left with an equation to solve, right? And this is an exponential equation. So we have to get the t out of the exponent, right? We have to get the t out of this power. And so how do we do that? Through the inverse, right? And so what's the inverse of the natural exponential function? Natural log function, right? So you just take the natural log of the side. So we have natural log of 0.5 is natural log of e to this power. And I don't know what the natural log of 0.5 is, but the calculator does, right? But here, these things on the left-hand side, right? The natural on the right-hand side, the natural log and the e cancel each other. So you have it's a very easy equation left to solve, right? Just minus 0.000432 times t is natural log of 5, and then just divide both sides by. Sure, you divide by the negative, right? Minus 0.0002. That should come out positive because it should be a positive amount of time, right? So if it doesn't come out as a positive amount of time, then that's a clue, right, that done something wrong. But it will, because natural log of 0.5 is a negative number. Your calculator will give that as a negative number. Then you divide by this negative number, the two minus signs will cancel each other, and you'll get a positive value. What does that turn out to be? 1600 approximately? Yeah. All right, so that's the half-life of radium. I just kind of knew that off the top of my head. It was 1600 years, or approximately. All right. Now, we haven't had a lot of problems like this one. Just this is really more of a college algebra problem, but I just threw it in here just to remind you of the quadratic. So here you've got a quadratic function. That's a polynomial function of degree 2. Quadratic functions are polynomial functions of degree 2, right? And it just says find the x-intercepts. Well, here at the end of the semester, right, we've been dealing a lot with finding x-intercepts of polynomial functions. So this is just another example of that. So to find the x-intercepts, right, you set y to 0. So you would put 0 into this formula for y. So you would get 0 is equal to x squared minus 4x minus 3. So what you're really trying to do is solve this equation. You might be able to solve that by factoring, but unfortunately, x squared minus 4x minus 3 doesn't factor. It looks like it might, but it turns out it doesn't factor. But remember, because this is degree 2, it's quadratic, right? You can always use what? Yeah, you can always use the quadratic formula. So the lesson here is just, of course, don't forget about the quadratic formula, right? So the a value in this equation is 1, the b value is -4, and the c value is -3. So just plug those values into your quadratic formula. So don't forget the quadratic formula for the exam. May not be asked to use it directly, but it may come up indirectly in finding roots of polynomials. So just substitute the values, right? And really, the hard part of using the quadratic formula is simplifying it. It's not substituting in the numbers. So we have minus and -4, that's +4. So we have 4 plus or minus the square root of -4 squared is 16. You have to be very careful with the second term, right? -4 times 1 is -4, times -3 is +12. So you get 16 plus 12 under that radical, divided by 2. So this is 4 plus or minus the square root of 28 for 2. And so that's really, in a sense, those are the two x-intercepts. One of them is 4 plus square root of 28 over 2, and one of them is 4 minus the square root of 20 over 2. But you can simplify this a little bit by hand if you want to, without using the calculator, because 28 is 4 times 7, and 4 is a perfect square. So you can extract from under that square root a 2, because the square root of 4 is 2. So you end up with the 2 outside, and then just the 7 inside the radical. So we have 4 plus or minus 2 times the square root of 7 over 2. And we get lucky here because 2 will divide into both of these terms in the numerator, right? 2 goes into 4 and 2 goes into 2. So we can break this down even further as 2 plus or minus the square root of 7. 2 goes into 4 twice. Here, these 2's will divide out. So there you have it. There are your two x-intercepts. One of them is 2 plus the square root of 7, and the other one's 2 minus the square root of 7. And then you can use the calculator to approximate those if you need to. So if you needed to graph those two x-intercepts, well, then you could use your calculator to figure out, you know, what's 2 plus the square root of 7 and what's 2 minus the square root of 7. But those are the exact values for the x-intercepts. All right. Try this one now. So find the inverse of this function. So this is kind of a logarithmic function, right? The function is 4 times the natural log of x minus 3. So we just have to remind ourselves here what's that general process for finding inverses, right? First, take the f of x, though. Take the f of x and put y instead of f of x. So we have y is equal to 4 times the natural log of x minus 3. So I haven't really changed anything so far. I've just written y instead of f of x. And now what's the strategy for finding inverses? What do we do? What were the steps? Swap the x and the y. So I get x is equal to 4 times the natural log of y minus 3. And now you take that new equation and solve it for y. So here we are in this position of getting the y out of the natural log. And we know we're going to do that eventually by using an inverse, right? All right, so at some point, I'm going to have to apply the inverse of natural log. What's the inverse of natural log, though? E. Yeah, right. It's natural exponential function. But before you haul off and use the e, first get rid of the 4. So divide both sides by 4 first. So you would have x over 4 is equal to natural log of y minus 3. And now you're in business. Just raise e to both sides. So on the left-hand side, you get, well, you just get what you get there. You get e to the x over 4. And then, of course, on the right-hand side, the e and the natural log cancel. So that would just leave you with y minus 3. And now all you have to do is add 3 to both sides. So there's your inverse function, e to the x over 4 plus 3. So you get this very simple inverse function, e to the x over 4 plus 3. That's the formula for the inverse function. So don't get thrown by the natural log. It's the same process of finding inverses as before, right? Switch the x and the y, and then solve the new equation for y. All right, let's see what 18 says. This looks like a transformation problem. So consider this function. Well, that's the natural exponential function, just e to the x. And we want to write a formula for a new function, h, so that the graph of h is the same as the graph of e to the x, except it's shifted to the right by 5 units and up by 1 unit. So how do we shift to the right and how do we shift up? How do we shift to the right? So what was the trick for shifting to the right or to the left? What? To the right is minus, right, of what though? What do you subtract from, Iris? What now? So if you're shifting to the right, you're shifting along which axis? Which axis there? The x-axis, right? So you add or subtract from x. You're right, and you're going to subtract. You shift to the right, you're going to subtract 5, but it's from the x. So right here, e to the x minus 5. So in that exponent, you're going to write the minus 5 with the x. And then how do you shift up? That's easy. Just what? Just plus 1, yeah. Just add 1 to the whole thing, okay? So that will shift it up. So those are very easy transformations, right? Just shifting up and down and left and right. Those are easy to accomplish. Wait, let's see. Well, let's try this one. We got plenty of time. So I skipped over this one, but let's just remind ourselves of this and see how this works out. 19. Okay, so well, we've done this a lot, right? So we should be really good at this one. There's a polynomial function, it's cubic, right? Okay, so but it's polynomial. And we want to use the rational zeros theorem, right, to write down all the possible rational zeros or roots or x-intercepts. Remember, those are all interchangeable terms. So we want to write down all the possible rational number x-intercepts for this third-degree polynomial, right? So what's the strategy there? Remember, you take all of the factors of 3, right? So how can you write 3 as a product? Not many ways, right? You would have what? And plus or minus 3, correct? Yeah, that's it. And then do the same thing for your leading coefficient, the 6. So you would have plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6, right? I kind of got out of order there. You have 1 and 6. That's one way to write 6 as a product. So you get plus or minus 1, plus or minus 6. And then you can also write 6 as a product as 2 times 3, right? So you have plus or minus 2 times plus or minus 3. And then you just have to take all of those ratios of all of these numbers divided by all of these numbers. So you have to make sure you get them all written down right? Well, you can take both of these and divide by 1. So you're going to get, as a repeating here, plus or minus 1 and plus or minus 3, correct? Now take all of these, divide by 2. So what does that give us? Plus or minus 1/2, plus or minus 3/2, right? And then take, is that it? So I get plus or minus 1, plus or minus 3, plus or minus 1/2, plus or minus 3/2, right? And then all of these divided by 3, correct? So it looks like you would get 1 over 3. So that's plus or minus 1/3 is a possibility. And then 3 over 3, though, is 1. We already wrote that. Right? Now let's take these and divide by the 6. So you get 1 over 6. So that's plus or minus 1/6. And then you get do I get them all? Yeah, 3 over 6 is 1/2, but we already wrote that down. Oh, so is that it? Okay. Oh, so there they all are. So we're hoping that if we have any x-intercepts, they'll show up in that list, right? And that's what part B actually says. It says use synthetic division to show that 1/3, it turns out, really is an x-intercept for this function. So let's use our synthetic division. So we write down the 1/3, right? Write down the coefficients of your polynomial. So you have 6 and then 13 and then minus 14 and then 3. Remember, if you're missing a power, be sure to put in 0 for that coefficient. So if, for instance, if the 14x weren't there, if you skip from 13x squared down to 3, be sure you put in a 0 in your synthetic division for that term. That happened on the test, and that threw people off on test number 3. Oh, by the way, let me, while I'm thinking about it, y'all can do that synthetic division really quick. While I'm thinking about it, for the people who are here, let me test number 3 back to. Okay, all the tests that I can give. Let's see what happens here. This one. Does this work? So you bring down the 6. 1/3 times 6 is 2. Add there. 13 plus 2 is 15. 1/3 times 15 is 5. Minus 14 and 5 is minus 9. 1/3 times minus 9 is minus 3. Yay, it works, right? Okay. So x equal 1/3 is a 0, right? And that also tells us, by the way, that this polynomial factors as x minus 1/3 times, let's see what's left here as our remainder from this synthetic division. It would be 6x squared plus 15x minus 9, right? So if you want to find the other x-intercepts, you can now restrict your attention to just what? The 16x squared plus the 15x minus 9, right? And you might be able to factor that one because it's only quadratic. If you try factoring, by the way, be sure you factor out a 3 first, because that would make the factoring easier. But that's not asking this question, but just remember that. Okay, so now let's finally get into, so here's some of the new things, right? Okay, that are in the last 2 homeworks that will be on the final exam. So this is a rational function. Remember, it's a rational function because it's the quotient of 2 polynomials. In the top, you have 4x squared minus 400. That's a polynomial. And in the bottom, you have 2x squared plus x minus 15. That also is a polynomial. Okay. First question, find the vertical asymptotes. Remember, when you graph rational functions, you often have vertical and horizontal asymptotes. And how do you find the vertical ones? So what's the trick? If you set the numerator to 0, Ravi, that's going to be the same as finding the x-intercepts. Why is that? Because look, to find the x-intercepts for any function, what do? You set the formula to 0, right? So you would have 0 is equal to 4x squared minus 400 over 2x squared plus x minus 15. But if a fraction is equal to 0, the only way that happens is if the top is equal to 0. So you can just forget about the bottom in this case, and you would have 4x squared minus 400 equals 0. So that's essentially setting the top to 0. That would allow you to find the x-intercepts. By the way, we can solve that because you can factor this. A 4 will factor out, so you would have 4 times x squared minus 100, but x squared minus 100 is the difference of two perfect squares. So that factors as x plus 10 times x minus 10. Oh, so there are your two x-intercepts, 10 and minus 10. It crosses the x-axis at 10 and minus 10. But that wasn't one of the questions. But that's a good thing to remember. So for this rational function, if you want to find the x-intercepts, just set the top to 0. Okay, and see if you can solve that equation. Remember, a rational function is the quotient of two polynomials. So when you set the top to 0, you're really just finding the x-intercepts of the top polynomial. But we know how to do that. That's like the problem that we just did, right? We have all sorts of techniques for finding those x-intercepts. To find the vertical asymptotes, Ravi, you set the bottom to 0. It's the bottom you set to 0. Okay. The vertical asymptotes, those are going to be those vertical lines where the curve is not going to cross. So those vertical lines where the curve does not cross, that means you have numbers on the x-axis which are not in the domain, of the function. And you already know if you have a fraction, right, and you want to find numbers not in the domain, you set the bottom to 0. So that's why we're setting the bottom to 0 to find the vertical asymptotes. So 2x squared plus x minus 15 equals 0. And then there's a quadratic equation to solve. We might be able to solve it by factoring, or we can always use the quadratic formula. I hope it factors, though. Does it factor? Let's see. To get 2x squared, you got to have 2x times x, right? So there's no question of that. And then let's see. Can we get an x in the middle? How do we get a product of 15? How do we get a product of 15? Let me see if I can get this closed. Yeah. Of course, it's 1 and 15. That doesn't look very promising. 3 and 5? How about a minus 5 here and a plus 3 there? Would that work? Yeah, I think it does, right? 2x times x is 2x squared. Minus 5 times plus 3 is negative 15. In the middle, you'll have 2x times 3, that's 6x, minus 5x. 6x minus 5x is plus x. So yippee, that does factor. So so now just set your two factors to 0 and solve. So 2x minus 5 equals 0. I think that means x is 5 halves. That is the equation for the asymptote. It's x equals 5 halves, because equations for vertical lines are x equal to a number. So one of your vertical asymptotes is x equal 5 halves. So Ravi, when you graph this, unfortunately, you don't have a graph of it. But when you graph this over here at 5 halves, about right here, yeah, the graph will not cross that vertical line. So you'll get some sort of curve, but it won't touch that vertical line. So that's going to give you a break in the graph right there. And also at, what's the other one? Yeah, x equal minus 3, right? So over here at minus 3 on the x-axis, you will have another vertical asymptote. The dashed line is the asymptote. That's not part of the graph, but when you graph the curve will not cross that dashed line. Okay. So that allows us to complete this. Oh, wait, no. This second part is asking us what's going to happen. Read this very carefully. It's asking us what's going to happen to this graph, this curve, as x gets really large or as x gets really small. Okay, so over here on the far left and over here on the far right, what's happening to the graph? What that question is asking you for is not vertical asymptote, but horizontal asymptote. Okay. You remember how to find the horizontal asymptote? That's where you look at the degrees. So Ravi here, the degrees are what? The same. So what do you do in that case? You just take the quotient of the leading coefficients. So the leading coefficients here are 4 and 2. 4 divided by 2 is 2. So what that tells you is that you also have a horizontal asymptote at y equals 2. So as you go further to the right or further to the left, I don't know what this curve looks like in the middle, but as you go further to the right or further to the left, this curve is going to get close to this line, y equals 2. It's going to start flattening out and looking like that horizontal line. So the answer here is y is approaching 2 as x approaches positive or negative t. Should have graphed that one, but I don't have Desmos open here to look at that. Is it oh yeah, it's -3. Right. If you wanted to express the vertical asymptotes like this, okay, you would say y approaches something as x approaches either of these two values. It could be 5/2, or you could say y approaches something as x approaches -3. Around the vertical asymptotes, the y values are either going to go to plus or minus infinity. Okay. So this around the vertical asymptotes, the graph is going to shoot up or fall off to negative infinity. So y is approaching either positive or negative infinity as x approaches 5/2. Y is approaching positive or negative infinity as x approaches -3. You have another question like that one? Whoops, nope. Let's see. I guess not. Okay, this is something now different. So this is a reminder of this is a reminder now of something very early in the course, right? So it wants us to find the area of this circle, find the area. So it's a geometry problem of this circle given by that equation. But it does give you a little hint here. It says the area of a circle is pi r squared, right? So it suggests use completing the square to put this equation in standard form. So use completing the square on this circle equation. Use completing the square on this circle so that you can find, well, you can find the center of the circle. That's not really useful to us here, okay? But what we're really interested in is finding the radius of the circle, right? So we can use that in this formula to compute the area of the circle. So this is really just a question about completing the square on a circle. So you remember how to do that? Let's see. You take your x terms, right? Okay, and group those, right? And then you take your y terms and you group those also, right, together. And that +1, pull that back over to the right-hand side. So that +1, that, and write it as -1 on the right-hand side. And then it's this part where you fill in the parentheses. This is the actual completing the square part, because you want to add a number in here so that this the expression inside the parentheses will become a perfect square. Same thing here. You want to add something in the parentheses, a number, so that the expression inside the second parentheses also becomes a perfect square. You know what number to add there, Iris? It's always plus, by the way, so it's always going to be positive. Yeah, so take 2, divide that by 2, and square that. So what does that give you? Pretty easy. That's what? No, it's 2 divided by 2. One, right? Yeah. So you're just going to put a 1 here. Yeah. Okay. And what about there? Same idea, Iris. Take the 6 divided by 3 and square that. So how much is that? 6 over. Yeah, that's 4. Is that 4? Oh no, I divided by 3. I'm sorry. I did that wrong. Yeah, it's always supposed to divide by 2. So you have minus 6 divided by 2, which is negative 3 squared is what? 9? Yeah, 9. Yeah, sorry, I wrote that down wrong. So, so we put a 9 here. Now you're guaranteed that these parentheses will factor. So this is going to factor as x plus 1 squared when you factor it. And the second one is going to factor as y minus 3 squared when you factor it. Oh, I forgot something. When you add the 1 and the 9, you got to keep the equation balanced. So be sure you put it on the other side as well. So when you add the 1 and the 9 in here, be sure you add them to the right-hand side also. Otherwise, you're messing up the equation, correct? And that means on the right-hand side, what do? You get 9. So that's easy. What's the radius now? 3, yeah. So the radius is 3. And the center, we don't really care about that, but since we can read it here, what's the center of this? What's the center of this circle? Yeah, exactly. Perfect. So now you can just take that 3, right, and put that into your area formula. So it's going to be 9 pi, I guess. 9 pi times 3 squared, 9 pi is going to be the area of this circle. These are some more transformation type problems. So here we're told these graphs are transformations of the sine curve. So these are sinusoidal curves. And we want to figure out what is the A value and what is the K value, so that if you graph this sinusoidal curve, you'd get this picture. So we've somehow shifted the sine curve, right? Or we've transformed the sine curve. What does adding K do? So Iris, you just told me that in the previous problem. If you just add K here, what's that going to do to the sine curve? It's going to move it, yeah. Which way? No, just up or down. It just shifts it up or down. If you want to shift or left or right, Iris, you have to add or subtract the K from X. Yeah, but here we're just adding it, not to X specifically inside parentheses. We're just adding K. So that shifts it up or down, right? Okay. And what does the A do? What does that change? Amplitude, right? Changes the amplitude, right? So what's the normal amplitude of the sine curve? It's 1, right? Let's see. Can we tell what this amplitude is? So remember, the sine curve goes up, the amplitude above, and then goes down the amplitude below. So what does this amplitude have to be here? Where's the middle of this sine curve now? It looks like it's at 2, right? And how far above 2 does this curve get? What's that? Can y'all read that? 5. So it looks like it goes up 3, right? And then also below 2, by 3. So I'm thinking the amplitude is 3, right? For this transform sine curve, instead of an amplitude of 1, has an amplitude of 3. But Ravi, it's also been shifted upward. And you told me by how much, right? Because where would that normally be on the sine curve? At 0. But now it's up at 2. So it looks like your k value there is just 2, right? Okay. So this must be the graph of 3 sine of x plus 2. Just that easy. What about this one? So clearly, instead of shifting up here, what have we done? Yeah, we've gone down. How far down have we gone? Well, we can tell, right? Because normally this point would be right here at the origin, right? Okay, but how far down is that? Yeah, now it's down at -3, right? So it looks like we've shifted it down by 3, right? Now, did we really change the amplitude at all? Let's see. So there's kind of the middle of the sine curve, right? How far up are we going? This is at 3. We're going up only to what? 2 and down to -4. That's only 1 again, right? So it looks like the amplitude is still just 1. Doesn't look like we've really changed the height of that sine curve, but something is different because normally the sine curve starts by going which direction? Up. But this one is going what? Down. So that means we flipped it, right? So this is -1. So the a value here is -1. We've reversed the direction of the sine curve, right? Normally the sine curve would go up and then come back down. This one is going down and coming back up. So we do have a little bit of a change in that a value. The amplitude is still 1, by the way, but that a value is -1 in this picture. So the formula for this is y equal minus sine of x minus 3. Here's an easy one for you. So a completely different problem. This has nothing to do with trig functions. So here we have a function called h, 2x plus 1 to the, what power is that? 10th power. So kind of an ugly function because it's got that big 10 power on it. And we want to break this up into 2 simpler functions so that when you compose them, you would get 2x plus 1 to the 10th power. All right, we've done this lots, right? So what are our candidates here for these 2 simpler functions? X to the 10th power, maybe for one of them, right? And then for the other one, Robbie? Just 2x plus 1, right? Now just check that. So compose these 2 functions. Remember, there's how you express composition, right? And see what you get. So let's see, what is g of x? We said, oh, that's 2x plus 1. And what does f do with an input? It raises it to the 10th power, right? So you would have 2x plus 1 raised to the 10th power. Oh, yeah, and that's the formula that we wanted. So there's our decomposition, just x to the 10th power and 2x plus 1. Now let's try just one more thing here. So this looks finally now like polar coordinates, right? So plot these points that are written in polar coordinates, and then let's see if we can convert them to rectangular coordinates. So we just have to remember, well, how to plot points in polar coordinates, but then also the formula for converting from polar to rectangular. Remember, those 2 formulas are x is r times cosine of theta, and y is r times sine of theta. The r value is the first coordinate in the polar coordinates. The theta is the second coordinate in the polar coordinates. So you've got to remember those formulas for converting from polar back to rectangular. Let's see. Let's plot these points though. We'll convert one of them to a rectangular. One is really all you need to see as an example. But let's plot them because plotting is always a little bit tricky. So 4 and pi over 4, where would that point be? Now, things have been made easier because we've got polar graph paper here. Okay, so remember the 4 is the distance away from the origin, right? So you can read that very easily off of this picture. 1, 2, 3, 4. Did I count right? 1, 2, 3, 4. So this point is somewhere on this circle, the circle that's distance 4 away from the origin. But of course, there are lots of points on that circle, right? So how do we know which is the one that we want? Well, it's the one that forms the angle pi over 4, right? What's the angle pi over 4? That's 45 degrees, right? So in other words, you're going to go at a 45-degree angle, a pi over 4 angle, right? 4 units away from this is called the pole, same as the origin in XY coordinates. So at a 45-degree angle, let's count 4. 1, 2, 3, 4. So that puts us right about there. So there's point A, maybe about right here. What about point B then? Well, let's see. We're at angle 3 pi over 2. Where is 3 pi over 2? What is 3 pi over 2? Well, how much is just plain pi over 2? 90. So you got 3 pi over 2, Iris. So you're gonna rotate 90 degrees, but 3 times. It's 270. So you go 90, 90, 90. Oh, so that's going to put you along this vertical line, right? Okay. At distance what? 6. So 1, 2, 3, 4, 5. Am I counting right? 1, 2, 3, 4, 5, 6. Right there, maybe. Right directly below the pole. There's point B. Now, C's got the trick in it because it has the negative radius. Okay. So, but we are going to be counting off 5 units. Question is in which direction? So you're going to go direction pi over 3. How much is pi over 3? 60. So you're going to go 60 degrees, which is something along this line, right? 60 degrees is about right here. But if this were a positive 5, that would be easy. You would just count off 5 in that direction. 1, 2, 3, 4, 5. So that would put you maybe right there. But because it's negative 5, you're going to go backwards. So go down this direction. All right. Make sure you're going kind of along the same line as that 60-degree line, but go backwards. 1, 2, 3, 4, 5. So it puts you, instead of up here, it puts you down there. Okay. But still on the same 60-degree line. If you draw a line connecting this point and this point, right? Okay. That line should be, you've done this right, that should be 60 degrees. Did that look like 60 degrees? I think I overdid it. That looks a little bit too fat, but well, anyway, close enough. So there's our point C. It's ends up down in the 3rd quadrant instead of up in the 1st quadrant. Let's try going in the let's try going in the other direction just for fun here. All right. So these are rectangular coordinates. Let's put them in polar coordinates. So remember, the formulas for converting from rectangular to polar coordinates is R, that's the R value in the polar coordinates, is the square root of the squares of your 2 rectangular coordinates, the square root of the sum of the squares of your 2 rectangular coordinates. And the theta is the hard one, though. What was theta? That was the inverse tangent of what? Y over X. But this is misleading. And so sometimes you can go astray here. It's this theta is the reference angle for the correct theta. So sometimes you have to make an adjustment. There's an example like this in the homework. I don't think I have an example here though in this on this sample test. Maybe we'll make up a problem. No. All right. Well, so let's try this one. So let's convert that rectangular coordinates back to those rectangular coordinates back to polar coordinates. So what's the R value going to be? The R value is going to be just the square root of 4 squared plus 4 squared. So easy. So that's what the square root of 32. So there's your R value. If you want to, you can write that as 4 times the square root of 2, but don't really have to. So our R value is 4 times the square root of 2, or just the square root of 32. Now, what's the theta? It's the inverse tangent of y over x, 4 over 4. So that's the inverse tangent of 1. That happens to be pi over 4. Pi over 4 is the angle whose tangent is 1. Oh, so that's nice. You just get pi over 4 here. So, of course, this is going to be messier, right? Converting from rectangular back to polar is going to be messier because it's going to involve inverse tangent. So that's going to make it trickier. Yeah, let me show you the example. Let me show you an example. What I mean. Suppose, let's look at the point 4 minus 4. I'm sorry, minus 4 minus 4. So here's the point, minus 4 in rectangular coordinates. And I want to write that in polar coordinates. I want you to observe that's in the third quadrant, right? That point is in the third quadrant. Okay, so you go through your steps. So you calculate your R. The R value is going to come out the same as it did for this point. You get the square root of minus 4 squared plus minus 4 squared. That turns out to be the square root of 32 again. So, all right, so that's easy. So there's the R value. And then for the theta, here's what you're thinking. You're thinking, okay, theta, that's easy. That's the inverse tangent of minus 4, the y value over the x value, which is also minus 4. So you get inverse tangent of 1. But when you calculate the inverse tangent of 1, either by hand or on your calculator, you get pi over 4. Get pi over 4. But where is the angle pi over 4? That's in the first quadrant. Yeah. See, pi over 4 is in the first quadrant. So, so you're going to write down, as the answer here, you would write down, if you're not paying attention, as the answer, you would write, okay, square root of 32 and then pi over 4. But that point is in the first quadrant, not in the third quadrant. So you're in the wrong place. So what is really the correct angle? It's not pi over 4. It's the angle in the third quadrant whose reference angle is pi over 4. What angle in the third quadrant has reference? So this is really the angle we want. What angle in the third quadrant has reference angle pi over 4? Well, let's see. So if we go half a rotation, that's pi, and then add on another pi over 4. What's pi plus another pi over 4? I think that's 5 pi over 4, isn't it? Yeah. So the correct point is square root of 32 and not pi over 4, because that's in the wrong quadrant. It's 5 pi over 4. So that's the bad thing about converting from rectangular to polar coordinates using this formula, you have to be careful about when you check your answer, you have to be careful about, did I put the point in the right quadrant? If I didn't, I have to adjust my angle. I have to adjust my angle to make sure I'm in the correct quadrant. Okay, let me oh, darn it, I've logged out. Let's try logging back into WebAssign. If I can find the, I just want to look at the polar, well, maybe also the, let's look at the polar coordinate homework first. So there's a lot of converting rectangular to polar coordinates. So not a lot, but there's some, right? And so again, that's where you have to be. No, when you're converting polar to rectangular, that's pretty straightforward. But when you're converting rectangular to polar, that's where you have to be a little bit careful and make sure that you get the angle in the right quadrant. So be careful about, let's say, problem number 9 and problem number 10, because notice those problems are in those points are in which quadrant? Third quadrant. So make sure when you write down your angle, you write down an angle in the third quadrant. All right, let's look at 11 and 12 though, because well, especially number 11. Let's see if we can take that. Let's see if we can take that equation, which is in rectangular coordinates, and let's see if we can convert that to polar coordinates. Okay, and then we'll also try number 12, see if we can make any progress with that one. I'm not sure if I have to think about number 12. Okay, so this is a rectangular form, right? That's in rectangular form. And so, and we want to put it in polar form. Remember, equations in polar form look like R equal to some formula involving theta. So equations in polar form look like number 12. Okay, you have R equal to some formula involving theta. Of course, you know what rectangular equations look like, right? Okay, they look like something like this, right? Where you have an equation with x's and y's. So, so we're trying to convert that back to something that looks like this. Now, look, when you have x squared plus y squared, though, that's kind of a tip-off, because remember, remember this. Do I have it? Oh, remember this equation, right? For converting from polar to rectangular, you have R equals square root of x squared plus y squared. If you square both sides here, then guess what? R squared is x squared plus y squared. But in this equation, that's exactly what you've got, x squared plus y squared. So instead of writing x squared plus y squared, what can you put in there? R squared. And now you have R squared equals 9, which means R must be equal to what? If R squared is equal to 9, what's R equal to? 3. Ah, that's it. There's your formula. Notice it doesn't have a theta in it, but that's okay. All right, it doesn't have to have a theta. So don't want it in uppercase though. So we just get R equals, that's very easy. We just get R equals 3. Yeah, let's submit it and see if that's correct. Yeah, see. So you just have to sort of notice there, oh, x squared plus y squared. Oh yeah, I remember that's the same as r squared. Now let's look at number 12. Number 12 is kind of backwards though. Okay, all right, because not kind of backwards, it's backwards from number 11, because here we have in polar form and we want to convert it to x's and y's. All right, so see, you have r equal to some formula, right, involving theta. That's the way we're given. We want to convert it back to something with x's and y's in it. But again, you want to be on the lookout for things that look like your conversion formulas. And notice remember these two conversion formulas, right? X is r cosine theta, y is r sine theta. So too bad I didn't have r equals, something with a sign in there, right? But let's see what we can do with this. So first, secant is not very useful. So let's try converting that back to sine and cosine. Secant is the same as what? Let me write this on. Let me write this over here so y'all can see. So I had what? R equals 6 secant theta, right? So my suggestion is get rid of the secant, because that's not going to be very helpful, I don't think. But how can you convert secant to sine and cosine? Secant is the same as what? Isn't that the reciprocal of something? Isn't that 1 over something? Ah, it's 1 over cosine. So let's rewrite secant theta as 1 over cosine, so that we have cosine instead of secant, right? Because we have a better chance then of converting that back to rectangular coordinates. So you have r equals 6 cosine theta. Now, I'm sorry, 6 times 1 over the cosine of theta. But it's not very convenient to have a fraction in here. So let's get rid of this fraction. How can you get rid of the fraction? Well, one way you can do is write it as secant, but we don't want to do that, right? Because that's what we just came from. So how else can we get rid of that cosine of theta? Multiply both sides by that, right? So multiply both sides by cosine of theta. So on the left-hand side, you get r cosine theta. And on the right-hand side, you don't get much. You just get 6, right? But see, this is where we get lucky. What is r cosine of theta? In rectangular coordinates, what is that? Remember what? That's x. So now, instead of writing r cosine theta, you can write x. So you're always looking for those kind of substitutions. Do I see an r cosine theta? Oh, if I do, I can put x. Do I see r sine theta? Oh, if I do, I can put y. Do I see x squared plus y squared? Oh, yeah, that's r squared, right? So there it is. There's your rectangular form. It's just x equals 6. What kind of curve is that? That's a line. Yeah, what kind of line, Robin? Vertical. Yeah, that's a vertical line. So so there's the formula for a vertical line in polar coordinates. It's easier in this is one that's easier in rectangular coordinates, right? Type that in. Why this thing keeps capitalizing on me here. So we have x equals 6, right? Hey, nice. Okay. Want to try this one? The next one, this one has a trick in it. Okay. Ooh, that's so close, right? If I had r sine theta, that would be y. But unfortunately, the r and the sine are separate from each other, right? Okay. So I can't just immediately put in a y, right? But this one has a trick in it. See, what was that? R equals 8 sine theta. So let me show you what the trick is. It would be nice if I had r times sine of theta, right? On the then that would be y, correct? So I'm just going to do that. Let's multiply this by r. But you have to keep the equation balanced. So multiply the left-hand side by r also. So you get r squared is equal to 8 times, I'm going to put the r in front of the sine. So if r squared is 8 times r sine of theta. But what is r sine of theta? Y. So now you can plug y in. And what's r squared? That's x squared plus y squared. So there's the equation in rectangular coordinates. It's just x squared plus y squared equal 8y. That happens to be a circle. So if you graph that, you get a circle. So r equals 8 sine theta. That's the in polar coordinates. That's a circle. Here it is in rectangular. So see, that did have a little trick there. You had to multiply both sides by r. Only reason I was thinking to do that is I wanted to have r sine theta so I could get y. And then I just lucked out because when I multiplied the left-hand side by r, I got r squared, which I could also easily convert to rectangle. Okay, well, it's like we exhausted our time here. Okay, so Wednesday is the test. I don't think it's too bad if you study the review and finish your homeworks. I think you'll be doing okay. Yeah, y'all have other questions y'all want to ask? Anybody online? I've sort of neglected y'all. Y'all have any other questions that y'all want to ask? One survival card. Yeah, one survival card. That's it. So make sure you put the highlights there on your survival card. And so yeah, we'll all be in here together. I don't think it will probably won't take the full time, but it might. I don't know, but we have plenty of time. So the period is 2 hours, but we can I don't think there's anyone here after that, so we went over that. We may be able to run over it. So I think we'll have plenty of time. All right, guys. See you on Wednesday. Study well.